Yes, sir. Start.
Hello and welcome to the live session for the course on GPU architectures and programming. So we will be taking a few questions from you in these live sessions. So feel free to post in the YouTube chat box and we'll be waiting for your questions. And also by the time for which you may be posting questions, let us do a small summary of the topics that have been posted in our forum. So we have tried to answer some of the questions related to various topics that have been posted in the forum, and based on those queries we have kind of created an idea that what are the different problems in which people may have got some issues. So let me just share my screen and just go through some of those issues which are commonly occurring among students. So I hope my screen is now visible to everybody. So we found that there are some issues related to hazards that occur in basic CPU pipelines. So, there is a gap in the understanding of hazards. So, please study that part carefully. We are just trying to highlight one of the possible. It's like the hazard that comes from true dependencies in. Our CPUs, right? So, suppose you have two instructions, instruction I and instruction J, I occurring before J, and as you can see that the ith instruction is an add instruction, which is adding register contents R1 and R3 and writing to R2. And the jth instruction is reading the values of R2 and R3 and is doing a subtraction, that is R2 minus R3 and writing that to R4, right? Now, if you observe here, there is a dependency through R2 between these two instructions. So J needs the latest value of R2, which is only available after ith instruction passes through the execution stage of the pipeline, and then it forwards it to the next instruction. So unless and until this dependency is resolved, jth instruction cannot go forward for its own execution, right? So if you see, we have this is what we call as a read after write hazard. So this read from R2 can only happen after the write on R2 by the preceding instruction has successfully been executed and the data has been forwarded, right? So that's why there is a read after write hazard. And if you study the basic computer architecture books and also our slides, we have provided you examples of this and also several other kinds of hazards. So that's one thing you should pay attention to. Now, the next class of queries we figured out were on branch predictors. So if you see in our exam, in our course material, there is this example of a 2-bit predictor taken through, which is being designed as a 2-bit saturating counter, right? So since it's a 2-bit predictor, I can encode 4 states of the predictor using the 2 bits. So the states can be strongly not taken, weakly not taken, weakly taken, and strongly taken. What it means is that as long as I am in any of these not taken states, so I will issue a not taken decision. But if the actual situation in the program is that the branch has to be taken, then I will move progressively to the taken states, and vice versa for the transitions from taken states to non-taken states. For example, if I am in weakly taken state of this a finite state machine, my decision would be not to take a branch, but if it, the decision would be to take a branch. But if the actual situation for the program is not to take the branch, then I also move from this state to a weakly not taken state, right? So suppose these are the actual branching decisions, 101010.
Sir,
Yes.
so the screen is not showing, the PPT is not showing actually, it's showing the black screen. Yeah, now it's showing.
Okay, so fine. So as you can see, this is a this is the 2-bit predictor. So there are 4 states. So just want to clarify these points. Like suppose I am in this weakly not taken state here, and there is, so if I am in this weakly not taken state, then then my branch decision is not to take a branch. But suppose right now for the program, the actual decision, the true decision has to be taken. Then from this I change state to a weakly taken state, and that's how all the other transitions work here. So just to clarify, if I am just moving through this kind of a actual sequence of branch decisions. So this is, I should be taking the branch, then I should ideally not take the branch, and so on and so forth. So let's say these are the actual branch decisions which should be happening, and I'm trying to predict them. So if I consider a 1-bit predictor, and the 1-bit predictor, let's say it starts from the taken state, that means first it should take the branch, right? And then after it takes the branch, it sees that, well, since it has taken the branch here, right? Since it is taking the branch because it's in the taken state, right? But then also, I mean, it's a 1-bit predictor, right? So what would happen is, well, for the next branch, again, it would ideally take the branch. So but that would be a wrong thing, right? So what will happen is, well, its prediction will then go false, right? But then since it's a 1-bit predictor, it will also go to a not taken state. Now since it's in a not taken state, right, for the next bit, again it will say that, well, let's not take the branch, which is again wrong, because the next true decision is to take the branch. So as you can see, in this way, I mean, after the first true prediction, all its predictions are going to be wrong, right? So just to summarize, initial decision was to take the branch, but then it went wrong, because then again it said that, well, you take the branch, and it was a wrong decision. So now it has switched to the not taken state, because it's a 1-bit predictor, so it's either taken state or not taken state. Now again, for its next state, it will say that, well, don't take the branch, which again is wrong, because now the third correct decision is to take the branch. So in that way, it will perpetually be in an out of phase with the actual decisions. So for it, the outputs will be taken, then again taken, then not taken, then again taken, then not taken, which is kind of after the first bit, all the complements of the other bits, right? So as you can see that after the first true prediction, all the subsequent predictions will be wrong, right? Now again, if I consider a 2-bit predictor for this situation, then what will happen? Well, the first decision would be true. Let's assume I'm starting from the strongly taken state of this predictor. Now then, let's say the next correct decision is not to take the branch, but since this one is in the strongly taken state, so it will say that, well, you take the branch, which will be again a wrong decision. But then again, it will move from the strongly not taken to the weakly taken, to the weakly not taken state, right? So then again, so again, there is another branch. So what has happened? If I just say again, so it's in a strongly taken state, right? So it's here. So it's here. So it will say that, well, you take the branch. So that's a true decision. Then for the next branch decision, it will again say that you again take the branch, but the true decision is not to take the branch. So from the strongly taken, it will go to the weakly taken state, right? So its decision is wrong, because it is saying that you take the branch, but the actual decision is not to take the branch. So its decision is wrong. But now it is in the weakly taken state, right? So again, if there is a branch decision, it is again going to say that you take the branch, and that coincides with the actual true decision, which is to take the branch. So now it will follow this arc, right? And it will again go to the strongly taken state. So true, false, and then again it is correctly predicting, and this sequence will continue. So as you can see that this is like correctly locking on with the alternating branch decisions. So clearly this is the worst case input I am giving, and it is able to correctly predict this pattern, right? So that's a small summary of branch prediction related issues that we have observed in the forum. Now, the other few questions were there regarding the graphics pipeline. So just to tell you that in this course, we are just trying to tell you what are the different components of the graphics pipeline which are there in the GPU, but we are not really delving into how that graphics pipeline is going to be used, because primarily we are focusing on how to do compute using efficient GPU programs. So I mean, how to accelerate graphics or workloads is not really the focus, as you can clearly see in the course content. Now, the other issue we found was how to specify threads mapping in the different streaming multiprocessors that are there in a GPU. So just to give you an idea, so you have these different streaming multiprocessors inside a GPU, and inside each streaming multiprocessor you have all these scalar processors, right? So for example, let's just look at here. So if you have streaming multiprocessor ID 0, it has got inside it a set of scalar processors SP0, a set of them, and I mean up to SP39, like that. Now when you are mapping thread blocks into these SMs, so one thread block doesn't get shared across two different streaming multiprocessors. And so what happens is, but again, you can have multiple thread blocks getting mapped into the same streaming multiprocessor. So we're just showing an example here. So let's say suppose the mapping is all two-dimensional mapping. So you have 2D mapping of blocks, and inside blocks you have 2D mapping of threads, right? So the block 00 and block 01, they are getting mapped into SM0. Each of them are going to consume 20 of these scalar processors. So inside them, they have got the threads, who are also packed in 2D in a 5x4 configuration. So the threads are being arranged with IDs 00 up to 43, right? So we are just trying to show that how threads are arranged in a two-dimensional setting of thread blocks, and thread blocks are again arranged in a two-dimensional setting of blocks, and how they get mapped into the different SMs, right? So just to show an example here. And then there was a few queries on thread divergence. So this is one topic you must study carefully because it's a performance limiting factor for GPUs. So ideally, when do divergence occur? So divergence occurs when all the threads which are inside a warp do not do not have to execute the same instruction, and that is being directed by the semantics of the program. So suppose the program has got a branch instruction where the branch condition is a function of the thread ID. And it happens that inside a warp, you have got 32 threads of different IDs, and some of them satisfy the branch condition and some of them doesn't satisfy the branch condition. So what will happen is the warp will diverge. Now, the threads which will satisfy the branch condition will progress together. And once they are done with that branch, then the other threads of the warp who have been waiting till now will actually go in and execute the other side of the branch. So considering an if else kind of statement, so the warp is getting serialized because all the instructions are not moving forward together, all the threads are not moving forward together. Those who satisfy the if part will move forward together, and then those who satisfy the else part will move forward together. So this is the kind of serialization that is happening, and it can happen in cascades because when we write programs, we can have conditional loops, we can have cascaded if else's, which can generate lots of divergence. So that is one issue we have to take care of. So that was my initial summary based on whatever questions we found in the forum, and we are now ready to take a few questions for you. So let's see if we have some questions here. So maybe we'll first check the few questions that are there in the earlier, in the Google, in the Excel we floated earlier. So Aditya Agarwal wants to know if we see growth in OpenCL with respect to CUDA. So, well, that's something really depending on the market and how these companies promote their stuff. For now, we can tell you that, well, CUDA has been really acceptable to the programming community because of its ease of use, and since many people for their workstation and server class computing are using NVIDIA GPUs, so the CUDA is the option they prefer because CUDA programs perform better in their target GPU systems because the systems are much more optimized. The CUDA compiler is much more optimized with respect to an OpenCL compiler targeting the same NVIDIA GPU, right? But there is a lot of scope for OpenCL. For example, OpenCL is a language for heterogeneous computing, so which is gaining quite a bit of popularity in the embedded domain, the mobile phone domain, the automotive domain, because OpenCL helps you to target different, target a system where you have, chips from the process CPUs from different CPUs, GPUs, and maybe some other processing units like neural processing units, all coming from different vendors, but all of them conforming to the same SIMD domain of computation. So, right. So, and that's the power of OpenCL, and that's going to be leveraged in all these embedded and automotive and these domains. And we see a lot, for example, if you consider mobiles coming from, let's say, Samsung's Exynos processor, so they support vanilla OpenCL. So they have OpenCL drivers provided, so you can actually port and run OpenCL applications in them. And also, the good thing is OpenCL has evolved into several other languages like SYCL and others. For example, Intel has got this DPC++ framework, which is kind of OpenCL based, and which also targets Intel CPUs and GPUs, right? So that's one area where OpenCL will also have growth, but definitely who will have how much growth, that's only for us to check, and we have to use these platforms. So next we have an interesting question on whether the very new NVIDIA architecture, the Turing architecture, they provide this facility for using floating point and integer operations in parallel. Yes, that is there, which was not there in some of the earlier generations of GPUs. So where there was some dependency between floating point and integer pipeline. So whenever the integer operation would be executed by some warp, then the floating some other warp which was going to execute some floating point instruction, that would get stalled. But with this modern variants of NVIDIA architecture, we see that these pipelines have become independent. So let's say you have a program where you have a sequence of instructions, some of them in floating point instructions, some of them integer instructions. And so there will be different warps at a time. Some of the warps are executing these integer instructions, some of the warps are trying to execute floating point instructions, and they can go in parallel and execute them, because in modern NVIDIA systems, these pipelines are kind of independent. So there is also a request from Uday to provide more examples on CUDA programming and all that. Surely we can do that. We will do that as we go ahead with the program. So similar request I also see from Deep Ganguly, who asks whether we can refer books on CUDA programming. So if you see our initial course proposal which is there in the NPTEL web page, so we have actually provided a name of few reference books for CUDA. But I can just say one good book right now. For example, if you are looking for the book or one book, let's say, so there is this book, Professional CUDA Programming, right? I mean, please look into that. It has got a lot of interesting optimizations and other programming examples for various kinds of problems, reduction problems and others. So please have a look into the book on Professional CUDA Programming. Again, we have a question. What is the difference between launching threads traditionally using, say, OpenMP and CUDA handling them exclusively? So these are different programming models altogether. So when we talk about OpenMP programs, so they are kind of more suitable for multi-core applications. When we say multi-core, we are restricting our attention to multi-core CPUs. For example, you have, let's say, a quad-core CPU, and you can write an OpenMP program which can parallelize a for loop and run it across this and parallelize it, run it across these different cores that are available in that CPU. Whereas when you are talking about CUDA, it's basically a language targeting a GPU system where the whole idea of what a core is fundamentally different between a GPU and the CPU system. So when we talk about a GPU system, we are considering very lightweight scalar processors as the basic atomic computation unit, which are stacked together inside what we call as a streaming multiprocessor, and we have several streaming multiprocessors sitting together inside a GPU. So we have a question here from Raman. We know that a block must execute in a single SM, but if the number of threads in a block is more than the number of SPs in an SM, then the block will execute in two batches. Is that correct? Why exactly can't a block execute across multiple SMs? Well, this you cannot do. That is, if the number of threads in a block is more than the number of scalar processors in a SM. So let's understand what is the philosophy here. Fundamentally, the size of block is restricted to 10324 threads per block. So if you see our course material, we clearly specify that. And the idea is that, well, you want to restrict the number of blocks and the size of the block, because I mean, you strictly speaking, inside an SM, you can have less number of SPs than the maximum thread block size. But the point is, when you are having a block mapped to a SM, it is not the case that all the threads in the block are going to execute concurrently. Like we have discussed in the course, that these threads inside a block, they will be packed into atomic execution units of warps, right? And some of the warps will execute concurrently, some of the warps will wait and all that. And this is managed by the hardware scheduler. So what is important is we have to remember for each thread in each of the warp, what is their thread context, what is their current execution status, what is the register file status for each of them. So as it happens, this memory limitation in each of the SM will constrain the total thread context that I can really remember inside one SM, right? And that limits the size of the block. So and that is and there is a related question: why can't a block execute across multiple SMs? Well, then the problem would be that if I allow a block to execute across multiple SMs, then I have to take care of synchronization of the threads inside the same block. Now we really don't want to do that. Why? Because we want, we have this facility of shared memory inside each of these SMs, right? And the shared memory is kind of transparent to all the threads inside the block, right? So this notion of having a shared memory which is transparent to each of the elements in a block, that is what we want to use when writing our programs optimally. Now, if we allow a block to spread across two different SMs, then if you just think in a virtual world, what would happen? Well, then the threads in a block will get access to two different locations of the shared memory, and then it really is difficult, right? Because then the idea that this block is looking to this shared memory location to which it has got access, but the other thread block that may be executing, it cannot access this segment of the shared memory where this guy is mapped. Those restrictions get hugely violated then. That's problem point one. Second point is we want to increase scalability. We want to give more freedom to the warps getting scheduled, right? So, and that's how we are arranging the system. We are arranging a high level block scheduler which is mapping the blocks across SMs, and we have low level SM schedulers who are scheduling warps inside blocks, right? Now, if we allow blocks to get partitioned, then this nice hierarchy and the scalability that this provides us will get lost. So these are the two reasons, I think, due to which we will not like to have blocks executing across SMs, because we fundamentally don't need that. Well, if I have more number of threads, I can split them into smaller blocks, and I can make them do the same work. And I lose this advantage of having private shared memories per block, right? And I have an increased overhead of managing the blocks across SMs. So that would be one of the reasons. So we'll be waiting. If you have any more question, please let us know. So do you have some more questions in the YouTube channel? So, Deep, we saw this question and we also tried to answer that there is a fundamental difference, like we said, between launching threads using OpenMP and CUDA. Okay, but what do you really mean by saying that launching threads traditionally using, say, OpenMP and CUDA handling them exclusively? So CUDA cannot handle the CPU threads, right? So OpenMP can launch threads in the CPU, and using a CUDA program, you have a host program part which will execute in the CPU, but it will launch the GPU kernels. It will launch the SIMD kernels in the GPU. But if I am assuming that, are you trying to say that using an OpenMP program, I am trying to launch multiple threads in multiple different CPUs, and then inside each of the threads we have a host program through which you want to launch CUDA kernels to the GPU? That may be problematic because it depends on the device, the type of the device, right? Suppose you have a single GPU and a four core CPU in your system. So fundamentally, you will have to have one host program. You will have to have one host program who will be launching some kernel for the GPU, right? So that host program can run in any one of the CPU cores. But let's say, I mean, if you are looking for some other programming paradigm, something like OpenMP, then it's a different thing. So there is a question on the subjective assignment of week 3. Can you give a more specific query here? Just typing in the chat like exactly what is your query, because we do discussion elaborately in the forum itself. So if you have a more targeted question, like this is the point I don't understand or something like that, please write it here. So regarding that subjective assignment, I mean, it is just a simple matrix addition, right? For which you have been provided an input-output format, following which you should be writing your program. Okay. So Ravanar has a question. Shaders are the same thing as GPU compute kernel. It seems like both are essentially programs running on a GPU. No, forget shaders, because they essentially are for the graphics pipeline, and we are not discussing graphics pipeline here. We are, for when we are talking about compute kernels, they are dedicated towards the GPU's compute pipeline. I mean, shaders are like separate graphics oriented programs which will excite the shader pipeline and make the graphics operations go fast. Well, they will be using similar techniques, but that's a different pipeline altogether. So Shantanu Ranjan Datta, can I call a set of kernels simultaneously from OpenMP? At a time, you can, first of all, you cannot call a GPU kernel directly from OpenMP. You need to have a host program. So, well, if your OpenMP, you are saying that that OpenMP thread you are running in the CPU is acting as a host program, that's fine. But you cannot launch many kernels I mean, so you are having many OpenMP threads, and each of them is launching one kernel, and so in that way you have got multiple kernel launches, but all of them are targeting the same GPU. That cannot happen. At a time in your GPU you can execute one kernel, unless and until you are using the feature of concurrent kernel execution, which will require you to have some different programming. I mean, some more advanced programming pragmas in place. But there is something interesting which you can do if you have seen our part on CUDA streams from the same host program. Again, the host program is a C code. It can be an OpenMP thread running in one CPU, which is acting as a host program, something like that. From that, you can launch multiple programs, multiple CUDA kernels in the parallel streams, right? Then you also have a semblance of concurrent execution, but all of them are coming from the same host program. And but I think I mean, in our current coverage, streams has not yet been opened, so it will get covered. And then how to use CUDA streams to launch multiple kernels in the same GPU in different streams from the same host program, you will get to know about it. So please don't confuse OpenMP, MPI, and CUDA and OpenCL. These are different programming models. The programming model for CUDA and OpenCL is fundamentally similar. They assume the same structure of SMs, SPs, shared memory, and all that. But the idea of OpenMP, which has been there for long back, it is something different. It is for multi-core CPU programming. So don't get confused with both of them. This is a course for specifically for GPU architectures and CUDA programming. So if you are doing OpenMP and parallel programming in OpenMP, that's more targeted towards homogeneous multi-core CPUs. If you have any further question, please post it in the chat box. So there is a question from Deep: how do libraries like TensorFlow and Keras leverage CUDA? So this is something which we will be covering in the last part of the course, where we speak about I mean, how you can be, I mean, you can write, you can port ML workloads. But well, in that part we will speak about these libraries, but fundamentally what we'll be teaching is, well, how all these things like neural network inferencing and training, they eventually boil down to doing a sequence of matrix multiplications and resolving their dependencies, right? So essentially we will try to help you know how you can write such efficient libraries as are available in the form of TensorFlow and Keras, right? Well, inside these libraries, all you will find is that they are having these CUDA or OpenCL versions of programs which implement efficient matrix multiplication routines, matrix transpose routines, and all those, right? So, I mean, whenever you are running these libraries, you have such efficient programs which are running, and by knowing how to write such programs, you can develop such custom libraries for your more targeted applications. So if anybody has any further question, please let us know. Okay, so how is debugging of programs on GPU performed? Well, one problem we see that the debug messages that we get from NBCC, they are often not very useful. But one thing which can be very useful for you is to use profiler and debuggers that NVIDIA provide. For example, the Prof system. I guess we have also covered a bit of that in our course, like how to figure out their execution information of a program, which can also help you in debugging the programs. And definitely you have a version of GDB. For example, I guess you are aware of the GNU debugger, right? Which is often used in Linux-based systems for debugging CUDA programs. So you also have a CUDA GDB using which you can debug such programs. So, and also, I mean, if you are really writing good programs in CUDA and you want it to be performance or oriented, you have to get yourself familiar with some profilers like NVProf, through which you get to know how much programming, how much memory bandwidth you are able to extract from the GPU card, how much parallel operations you are able to do, what is the CPU, what is the GPU utilization you are able to achieve, what are the weak links in your program, where you have got more stalls happening, all this stuff. And also using the profiler for improving the performance is something we have also tried to show you using this some parts of the course, right? And specifically I think the transpose part. And also the debuggers I mentioned, like NVIDIA's debugger, the GDB version, which you can use in Linux environment. And similarly, NVIDIA also offers you such debuggers for the Windows environment as like plugins for the Visual Studio environment. So we have another few minutes. So if you want, you can ask further questions. Okay, so since there are no further queries, so then we'll be closing this session. Thank you for being here and asking your questions.